extreme hurricane cycles in places many of us would never expect. As we migrate to our eastern shores in record numbers, are we about to experience the deadliest hurricane supercycle ever known? Since the 1970s, the quietest hurricane period in recent history has fueled an unprecedented migration to America's East Coast. Generations of people unaware of the murderous punch of a high-category hurricane.
In the 1960s, there was a relatively inactive period, so the migration to the coast really increased when it looked like the threat from incoming hurricanes no longer existed.
People live their lives day to day. They don't live their lives on a global scale.
People are pretty complacent when it comes to preparing for hurricanes and getting out of harm's way because they just haven't had an experience with a really bad one.
Then something happened 2.5 months into an uneventful hurricane season. On August 17th, 1992, Chris Lancy, a graduate student at Colorado State, observes a tropical depression upgrade to a tropical storm named Andrew.
And my guess was that it was going to fall apart and, we'd never hear anything more about Andrew.
The event proves otherwise. In 5 days, Andrew's winds clocked 74 miles per hour, an official Category 1. The next day, it hits Category 4, gusting at 150 miles per hour. Rapid intensification generally means a 2-category jump in a day. Andrew jumps 3 categories. The P-3 Orion, or Hurricane Hunter, is dispatched into Andrew's eye. Its mission is to observe and measure the storm as it feeds off the warm ocean, and to help forecasters predict its course and know when to sound the alarm.
Okay, flight, I want you to track 270 right now.
Flight Director Barry Damiano.
With sometimes associated to a police officer chasing a crook.
The crew observes Andrew's eye wall, a ring of thunderstorms surrounding the calm eye, where the winds are most powerful.
It's a very strong storm of a Category 4 or 5 intensity. The eye can be very clear, and you would have a spectacular shot of the sun shining through with the light shining off the inside eye wall of the storm, which is sometimes conflicting for me because it's going to make landfall someplace and cause a lot of catastrophic damage.
Andrew's tsunami-like storm surge, up to 23 feet high, kills 3 in the Bahamas below. The plane transmits to this building in Miami, home of the National Hurricane Center, part of the National Weather Service and the National Oceanic and Atmospheric Administration.
Aircraft reconnaissance, investigating the system based on all the data we're looking at.
Here they look for answers. What's the size of the hurricane, its structure, and more importantly, where's it headed? Andrew unexpectedly re-intensifies just hours before making Florida landfall. On board the plane, the flight crew is convinced the only place for this storm to go is west. The National Hurricane Center makes it official. Florida evacuates 700,000. The National Hurricane Center takes a direct hit. 12 stories above its parking lot, its 2,000-pound radar is tossed like a play toy. Andrew takes 26 lives and costs over $26 billion in damage. Government officials rethink emergency plans, and scientists begin to revise what they thought they knew about hurricane intensity.
Miami, a place where I grew up, was my home as a boy. It looked like it was bombed out.
Three years after Andrew, the National Hurricane Center's new office is all concrete and steel. floodproof and windproof, eerily prepared for the future. Today, Dr. Chris Landsea is Science and Operations Officer. Since Andrew, the probes dropped into subsequent storms have become more precise. Newer GPS versions read sea level winds with more accuracy. This new knowledge has reopened a post-mortem analysis of Andrew.
What these dropsondes showed us kind of surprised us, because it turns out there's stronger winds right at the ocean surface in strong hurricanes we thought before. And that's part of the reason we've been reanalyzing hurricanes, and we upgraded Andrew from a Category 4 to a Category 5 based on this new understanding of the winds.
That took 10 years. So recent is the improved study of hurricane intensity, it took a full decade after Andrew for the National Hurricane Center to reclassify Andrew more accurately. And Landsea's records have revealed something else, a discovery with serious implications, a deadly cycle of increased Atlantic hurricane activity that persists through to the present.
The intensity has increased in the Atlantic. We've seen a big jump between the 1970s, 80s, and early 90s, where it was relatively quiet, and the number of major hurricanes was about 1.5 per year. In the last 12 years, we've seen about 3 to 4 major hurricanes per year. So it's been a big jump in the Atlantic. What this graph shows is the difference between quiet periods.
On the left, 50 quiet years, 8 landfalling hurricanes on record. On the right, a 250% jump. Florida, the Carolinas, New England.
The scientists were being asked a couple questions. First, what's the cause of these big jumps in activity? Is it natural or is it man-made? And also, what's to be expected the next 10 to 20 years?
Is this upcycle of Atlantic hurricane intensity and frequency a modern-day phenomenon? Can we tie it to climate change? One way to find out is to dig into records of the ancient past. But there's a problem.
We're missing one key tool, and that was the satellite imagery. It wasn't until 1966 that we had everyday satellite depictions. So it does make it difficult comparing the current busy period the last time it was busy, because we did not have those satellite images available.
Landsea's modern record alone is too short to tell whether these patterns are a repeat of ancient cycles. With an increased risk of Atlantic coastal strikes, governments and business have questions, and they look to science for answers, even in unlikely places. Here in a Georgia bog, this climatologist wades through some clues. Below his boots may lie records of ancient hyper-hurricane cycles, never before recorded, in the heart of dead wood.
This is very much detective work. This is, in fact, a lot of the principles we use comes from the study of forensics. In this case, the culprit is a hurricane.
Dr. Henry Grissino-Mayer is a dendrochronologist. Through wood alone, he's recorded 1,000 years of wildfires, climate patterns, and even authenticated antique violins.
Now, I don't think there will be any end to the amount of information that you can obtain from tree rings.
But extracting evidence of ancient hurricanes within these rings is not easy. In 1998, he searches for a hurricane signal, clues of hurricane rainfall within certain annual rings that look distinct from normal rain. But it's impossible to find that in the wood's physical properties alone. Grissino-Mayer needs to isolate the chemical difference of hurricane rainfall to crack the code. After setting up at the University of Tennessee, his answer lies waiting, just down the hall in Dr. Claudia Mora's isotope lab.
When Henry started talking about the possibility of a hurricane, a singular signal in the tree rings being captured, I just had to go look.
Mora is a geochemist who believes the hurricane's fingerprint lies in the oxygen content in the form of oxygen isotopes. If they can extract the isotopes from each year and measure their differences, they may be able to record on-again, off-again hurricane cycles.
It took about 1.5 years before we had a sufficient data set to actually look and say, wow, this works.
This is cutting-edge stuff. This hasn't been done before.
Perhaps this new information will lengthen our hurricane record back centuries before satellites. Ancient evidence of repeated cycles may better prepare us for our future.
It's only going to get worse. It may get worse because the intensity is increasing. It may get worse because the frequency increases. But it certainly will get worse because there are simply more people in harm's way.
High category landfall, sudden intensification, extreme rainfall, combined with an upcycle of frequent storms. These features combined could form the signature of a superstorm, a hyper-hurricane about to strike our Atlantic shores. Until 1992, storm records showed a downtrend in Atlantic hurricanes. Then Andrew, a rare Category 5, made Florida landfall. It changed the rules on how science studies such killer storms. By the mid-1990s, an increase in high-category Atlantic hurricanes began to pelt coastal communities. In 2005, the year of Katrina, the National Hurricane Center exhausted its pre-season list of 21 names for Atlantic storms. This rise in frequency and intensity sparked international fears that a supercycle of hurricanes will soon strike another major city, this time in unexpected places further up the coast. So scientists like Dr. Henry Grissino-Mayer were given a challenge to find evidence of ancient hurricanes, reveal their cycles, and see if they resemble the pattern that threatens us today.
So now what we're using, the tree ring record, is to learn about past hurricanes by actually picking apart the tree rings on a much finer scale to learn about past hurricanes, not only for the 20th century, but for many centuries.
Oftentimes at the top of these hurricane deposits, he finds a thin layer of charcoal that's been...
Much like forensic scientists, we actually use patterns in the tree rings, just like fingerprint patterns. We use the patterns in the tree rings from the living trees, and we overlap that pattern with the pattern of tree rings from the dead trees. And that's how we're able to assign years to the tree rings from these dead and down pieces of wood.
It starts with Grissino-Mayer's favorite, the longleaf pine, a native tree that once made up the lush coastal forests of the Carolinas, until the demand for ship masts and turpentine decimated their numbers. This tree is hurricane-proof and outlives many of its neighbors. Its wide root mat quickly draws up water which it incorporates into its growth layer, manufacturing cellulose in the process. The composition of the oxygen in the water that makes up hurricane rainfall is distinct.
So they essentially are drinking hurricane juice, if you will, and incorporating the water from the hurricane. The oxygen in the water from the hurricane is used when the tree makes cellulose.
Within that cellulose lies the hurricane signature in the form of oxygen isotopes, the chemical signature Grissino-Mayer is looking for. Claudia Mora merges disciplines with Grissino-Mayer to get at the hurricane story embedded in the wood.
We're working on the lake wood here, and what we're trying to do is fill this off.
So we're just trying to find that cellulose that's being made from the water drawn up and retains that hurricane signal. Because oxygen is in just about everything, it's really just a tool for a clever chemist to use.
Grissino-Mayer shaves a cataloged ring. Mora chemically extracts the cellulose. Packing it into a tiny ball, she fires it through a mass spectrometer. It separates two distinct types of oxygen isotope, one weighing more than the other, atomic weights of 16 and 18. The composition of lighter and heavier isotopes in hurricane rainfall differs from normal precipitation. A hurricane relies on repeated condensation for energy. water vapor rises, condenses, and forms a cloud droplet. This droplet falls as rain, and it takes with it more of the heavier isotope. It leaves behind more of the lighter isotopes, which still circulate in a vapor state.
If you take a rain cloud and you wring it a little bit, there goes some of the precipitation. You get a lot of the 18O falls out. You wring it a little bit more, well, you still get more 18 out than 16, but the relative amount has changed a little bit. There's just not as much 18O left. By the time it hits the land, it's very different than normal precipitation.
After a year and a half processing and recording centuries of tree rings,
the day we figured out that it worked, it was Miller time.
A season-by-season record of hurricane cycles that date back 4 centuries reveals ancient on-again, off-again patterns. It confirms that our current active cycle may not be an anomaly. The East has been battered again and again by hurricane cycles that may have lasted decades at a time. But how strong were these hurricanes? What about their intensity? Rainfall signatures can tell us that we've been hit. To learn how hard, we need to dig deeper.
So this will sink into the sediment, we'll release this, and the stopper will stop on the top, and it'll be like putting your thumb on the top of a straw, and then you'll lift it back up.
This crew looks for ancient storm surge signatures at the bottom of this inland pond in Cape Cod. The deluge from the hurricane storm surge is a tsunami-like flood that kills more people than the winds themselves. This pond lies within a half a mile of the ocean. At the bottom lie layers of marine sediments carried in by ancient storm surges. The team drops coring devices, searching for clues that date back far beyond tree rings. This operation is not hit and miss. In a nearby parking lot, a government van remotely controls and monitors a floating robot called Iris. Equipped with sonar, Iris captures pictures of the lake bed, showing the crew exactly where to look.
We're looking at a core that was collected at the deepest part of this lake. This core is about 6 meters deep.
Dr. Jeff Donnelly at Woods Hole Oceanographic Institute at Cape Cod heads the operation. He reconstructs hurricane data through storm surge deposits, creating a sort of war map of the East Coast, extending the hurricane record back thousands of years.
Storm surge is really a function of the wind piling water up against the coast. So between the onshore winds and this bulge of the sea surface because of the low pressure gives you the storm surge.
In this wave tank, the swell hits the beach and pushes inland, taking with it sediment from the ocean.
We have about 1,000 years of a record of storm surge washing over the beach at this particular location. It's your own little time capsule. It takes you back thousands of years potentially.
A 6-foot core represents about 1,300 years of history, data that Donnelly uses to reconstruct a calendar of hurricane events, their size, and the climate conditions that may have caused these active hurricane regimes.
This is a sand layer that was deposited by a storm, and based on the depth we're at, this is probably 1,300 years ago or so. We can confirm that by radiocarbon dating these plant remains.
The sediment core is basically a time machine. Its layers tell a story of storm cycles.
So here we've got the organic-rich peat that we were standing on in the marsh, but below that we've got these sand layers that have been washed in from the beach during the storm surge events. This whole record goes back probably about 1,300 years.
This is Jeff Donnelly's newest device, the XRF. It's an X-ray fluorescence core scanner. They call it the tricorder. As with Gracino Mayer's tree rings, it looks for changes in chemical composition within the layers.
For example, the marine sediments tend to be higher in elements like strontium and calcium. And so there's a very distinctive elemental signature that we can look at and determine basically the source material and know whether it's a storm surge event or a precipitation event. And we're coming up with some intensity estimates, at least in terms of the amount of surge that would have been required in order to deposit those layers.
Deposits within these core samples stretch the tree ring record of landfall events back further over millennia. They reveal brutal hyperhurricane cycles that struck repeatedly over the last 2,500 years, marked by inland coastline deposits hitting now crowded areas few would ever suspect. Storm surges from hyperhurricane events that topped every beach from Cape Cod to Long Island.
And often when we're out doing our work, we will talk to people and tell them what they're doing. They think we're crazy. You know, we don't get hurricanes here. We get a winter storm, but we don't get hurricanes. And of course, you know, we know from the historic information that, yeah, you do get hurricanes here. For example, there was a hurricane around 1400 AD, which appears in just about every core that we take from Long Island to Cape Cod.
This model can recreate and forecast the effects of a storm surge in flood-prone areas for evacuation planning. America's Northeast, 1635, 1815, 1938. The Northeast today, where 50 million people have never experienced a direct hit.
The Northeast is really susceptible. It's kind of sticking out right into the main hurricane belt as the storms are recurving up the eastern seaboard, particularly New England is basically sticking out right into the path of these recurving hurricanes. People have very short lives and very short memories, and it could be that we go into a climate regime where we get them much more frequently, and rather than you may or may not see one in your lifetime, you may see 2 or 3 in your lifetime.
Exactly when, he can't say. Sudden intensification, unexpected targets, unpredictable frequency. Science still struggles to find definite answers. And scientists don't like surprises. Owen Kelly claims he can predict within 6 hours when a hurricane is about to burst into hyperdrive. Dr. Len Pietrafesa bets that he can find order in apparent chaos and forecast the probability of an entire season. If he's successful, maybe we'll know when to get out of the way before the hyperhurricane returns to change our busy shoreline as we know it. Orbiting satellites keep a round-the-clock vigil on hurricanes down below. Tracking is very detailed, and forecasting their path is improving. But despite this coverage, predicting hurricane intensity is not easy. If coastal cities could get a better warning of when hurricane wind speeds are about to suddenly increase, they might better prepare for a stronger storm.
That's the case with hurricanes. It's always something tricky.
Intensity change is still a mystery. If there was a way we could have predicted Hurricane Andrew's surprise spin-up, might the losses have been different? In 1992, there was no way to tell. But now Owen Kelly believes he can predict a hyperhurricane's sudden outburst just before it reaches its deadliest point. This is NASA's Goddard Space Flight Center in Greenbelt, Maryland. It's where they design and monitor satellites. Kelly's work began with this 1958 publication by Dr. Joanne Saffer Simpson about her theory of short-lived, supercharged thunderstorms that spire high above the hurricane's eye wall. They're called hot towers. Kelly's real work began with the launch of a Delta rocket in 1997. On board a satellite called TRMM, the Tropical Rainfall Measuring Mission. It's equipped with a radar device that changes the way we look at weather. For the first time, 3D weather shots, like a hurricane CAT scan, capture a hot tower rising from the eye wall toward the stratosphere.
In the back of my mind, I secretly want to believe that these little, lone, tall thunderstorms
that are maybe 10 kilometers across compared with a hurricane 300 kilometers across somehow are giving the hurricane a kick.
50 years ago, laboratory observations like these were based on a simple premise: warm things rise. On the left, a theory that a hot tower rises like a bubble. On the right, that it rises like a plume. A hot tower's vigorous upward motion lasts about 20 minutes, roughly the time it takes for air to travel up 10 miles.
It's a principle that drives the circulation of the atmosphere.
Whether rising as a warm bubble or plume, a hot tower packs a punch that supercharges a hurricane. To understand a hot tower is to see the hurricane as a massive heat engine. This warm column draws surrounding air into its base. The less dense air rises, creating energy that drives this pinwheel. A hurricane's eye wall draws in moist vapor from the warm ocean surface. Surface air spirals in and rises rapidly. As the vapor condenses into rain, it releases heat energy, which intensifies the hurricane.
Every gram of water vapor that condenses is 2,000 joules of energy added to the atmosphere, so it's a lot of heat.
The hot tower releases more energy in a shorter time, acting like a supercharged piston in a car engine. The sudden burst of surface air drawn up into its column is much faster, causing greater wind speed.
What makes a car go faster is that you've depressed the gas pedal, so the fuel injector is adding heat more quickly.
Kelly hopes that his research becomes a common forecast tool to warn that a hurricane is likely to intensify within 6 hours of a hot tower sighting.
I have been talking with some researchers and some forecasters at NOAA, the National Atmospheric and Oceanic Administration, and they've given me some challenges of things I need to do to convince them.
Images of Katrina showed several hot towers during its development, yet this technique is not yet an accepted forecast tool. Until it is, this type of warning won't make it to the daily news.
If you've got continuous radar measurements and you see a sequence of towers, as the hurricane's approaching land, you should expect intensification. There's an 82% chance it'll intensify.
82% chance. Probability. What do we really know? Forecasting is about probability. Chances of a future outcome based on a combination of seemingly random events. The birth of a hurricane itself is unlikely. Many variables must combine at the right time and at the right place. This is Isabel at its birth in East Africa. Mountain peaks interrupt fast-moving air, creating large swirls of turbulence downstream. Only if atmospheric conditions are right do these eddies make it across the sub-Sahara to the tropical Atlantic. If ocean conditions are right, thunderstorms develop. Then, if the storms join up, they can begin to organize themselves into the familiar spiral of a hurricane. In this tank, water begins to drain. The energy of the main vortex draws random eddies toward its center, like random thunderstorms that spiral into the eye wall of the hurricane from the outer parts of the storm.
So in order for a hurricane really to get going, it has to have this very deep convection, at least 10,000 meters, and then all the storms sort of euphemistically say, hold hands and dance in a circle and get going into an organized hurricane, which draws in moist ocean air from thousands of kilometers away to fuel the hurricane.
Climatologist Dr. Jim O'Brien helped pioneer the forecasting of El Nino, another crucial chance factor that impacts hurricanes.
El Nino makes the environment in the Atlantic rotten for hurricanes.
An El Nino event forces the jet stream down into hurricane territory. Its high-altitude wind shear chops off the hurricane's upper cloud layer, effectively killing it off. Back to the journey of Isabel. Since there was no El Nino event in 2003, Isabel strengthens, undisturbed. Isabel's big chance for landfall depends on the predictable storm path of this high-pressure system, the Bermuda High, a sort of hurricane goalkeeper. It can deflect an active hurricane. Its pressure forces a hurricane to skirt the Bermuda High's edge. If Its position is key. It sends Isabel to North Carolina, the state's deadliest and costliest event of 2003. The culmination of all these events may seem like chance, but Dr. Len Pietrafesa doesn't see it that way.
My belief is that these systems, in fact, obey fundamental laws of nature, and so, in some sense, are deterministic, that they're well organized. They're not just random and chaotic.
North Carolina State University at Raleigh. Dr. Len Pietrafesa lives here, home of more billion-dollar hurricanes than any other state. His mission is to try and predict when and where they'll hit again. From seemingly chance factors, he looks for organization in hurricane activity.
It's the job of the scientists and the mathematicians to figure out how they have been organized in the past, how they are organized presently, and what this will mean for the future.
Pietrafesa turns to the total hurricane record to find discernible patterns, such as annual and decadal cycles, how many hurricanes formed in those periods, their pathways, and how many made landfall. He then looks for relationships in those cycles to changing climate patterns. What was El Niño doing? The oscillations of the ocean currents, the Bermuda High. He's seeking a sort of wiring diagram that makes sense based on probable outcomes.
And given that fact that we have found that they are organized and that they do travel in packs or clusters, and they take preferred paths during different seasons, which are related to different relationships of the climate factors.
Where Owen Kelly's hot towers give us a 6-hour warning to hunker down before a hurricane goes to hyperstatus, Pietrafesa wants to warn us way in advance what to expect the entire season ahead.
We made an announcement that 5 hurricanes would form in 2006 and that only one would make landfall, which at the time was considered to be a laughable forecast.
He nails it. In fact, 5 hurricanes did form in 2006, and one, Ernesto, did make landfall. Pietrafesa admits that a perfected system is still a few years away, but as he observes the interrelation between oceanic and atmospheric patterns, he now voices new concerns.
As we keep warming this planet, we're raising the stakes, and we're undoubtedly raising the potential for more and bigger events.
Pietrafesa views the planet as one giant Earth engine, conveyor belts of currents that distribute heat around the planet, a climate control system.
The amount of solar energy that the Earth absorbs on a daily basis is several times the amount of energy that can be derived from the total reserves of oil, gas, and coal on this planet. And that's per day.
Without these heat distribution systems, the tropics would boil. The polar regions would be permanently locked in ice. The hurricane is an express system that moves heat away from the tropics, an air conditioning unit that keeps the planet alive. Out here, in the waters off Bermuda, alarming data is being retrieved from the depths. Decades of ocean records may be revealing conditions that are about to fuel hyper-hurricane activity as they have in the past.
It may be that we're beginning to enter that era where we need to revisit the Saffir-Simpson scale and start thinking about category 6, 7, 8.
Our oceans are heating up, and they may be fueling increased hyper-hurricane events that work to regulate our warming climate. Unfortunately, more of us than ever stand in the way. A deadly cycle of hyper-hurricanes threatens to strike us again. We've altered our world and increased our risk. Can we control hurricanes? Some independent thinkers have ideas. A nuclear blast to kill off a hurricane, even though the largest warhead delivers only a fraction of a hurricane's power. Use giant fans to blow hurricanes away. drop ice into its eye, tow icebergs into their path. Chris Lancy has heard them all.
But it turned out you'd have to have all the vessels in the world towing icebergs all the time to cool off the waters enough to kill the hurricanes.
How about this diaper-like material that absorbs 2,000 times its weight in water? It loads up on moisture as it falls to the sea.
And even if you did take all the water out momentarily, the oceans are still evaporating all the time. That water would be replaced in about a day, probably less. So that wouldn't do anything.
The most infamous plan, the government-backed Project Storm Fury of the 60s and 70s, the days when enough money and technology seemed to be the answer.
And the idea was to fly around the hurricane in the periphery and launch silver iodide into the clouds. And the idea was that the silver iodide would take any supercooled water and instantly turn it to ice. And that releases heat of fusion, and that would help grow the thunderstorms in the outer part. So you make the outer part stronger and you kill off the eye wall. That was the theory.
It turned out that hurricanes did that on their own, as witnessed in Hurricane Andrew.
Andrew in 1992 went through an eye wall cycle when it was over the Bahamas. And it finished that eye wall cycle, weakened a little bit, and then re-intensified right when it hit Miami again. This process happens, but it's a natural process.
Project Storm Fury was disbanded. The bottom line? We're unable to control a hurricane's killer forces. But unfortunately, we're reshaping our world, inviting disaster, as we change our shorelines and create conditions for the hyper-hurricane's worst effects.
Not only have we moved in greater numbers to the coast and built more and more expensive housing, but we've also bulldozed and eliminated many of the natural systems that were there. For example, the maritime forests and the wetlands.
Maritime forests used to act as a buffer, protecting the inland from high-category winds. Now the winds move in unrestricted. The forest used to absorb the storm surge and dissipate the energy of the waves. Today, much of this protection is gone. Barrier islands, the shoreline's ancient defenses, have lost their effectiveness. In this tank, as with much of our shores, the forest and wetlands are gone. The storm surge advances.
Well, once the surge comes in, you start blocking roadways and start losing bridges, and it becomes impossible to move people.
On land, our modified coast sets the stage for unimpeded storm surge disasters. Offshore, the state of our oceans may set up the conditions for hyper-hurricanes headed our way. The clues lie out here, off the coast of Bermuda, aboard the research vessel Atlantic Explorer.
I come out to sea every month, that means I am a mad scientist.
Their mission? To collect water samples from the depths every 2 to 4 weeks, as they have for the last 53 years.
So this is our CTV, it stands for Conductivity Temperature Index.
From this stretch of water comes 50 years of data, a multi-decadal record of changes in the ocean that may help suggest why we've headed into a hyper-hurricane regime. Hurricanes need an ocean surface layer of 82 degrees Fahrenheit or higher to sustain them. It's some 300 feet deep. It's where scientists observe changes.
That's an observation that is important to the ocean's response to climate change.
Nick Bates is senior scientist at the Bermuda Institute of Ocean Sciences. His findings confirm a 0.5 to 1 degree warming of the upper ocean in the last 50 years. Enough, according to Bates, to lengthen the hurricane season.
Instead of the 1950s when perhaps we had a warm mixed layer of maybe 4 months, it's now extended to perhaps 4.5 months. Basically, there's more fuel, more heat energy for them to maintain their strength, perhaps build their strength.
Another clue that warns of a warming ocean lies in the ocean's phytoplankton. These tiny ocean plants absorb more than 100 million tons of CO2 from the atmosphere per day. This makes the ocean an efficient carbon filter, cleaning our atmosphere of heat-trapping CO2. But according to the data gathered from this and other research vessels, the plankton population is threatened in a warming sea surface layer. It's a potentially alarming cycle. Fewer plankton to absorb CO2 means more CO2 remains in the air. The warmer the planet gets, the hotter the ocean. So with insufficient plankton, hurricanes, which can act as nature's cooling systems by transporting heat northward, may increase in frequency and intensity. A planetary air conditioning unit working overtime, like it may have done long ago, before so many of us stood in the path of a hyper-hurricane event.
The air conditioning and the heating units were working together to try to redistribute heat on the planet, and they had to do it in a far more ambitious way than is even being done presently with our hurricanes.
And of course, now we're worried that human modification of the climate is going to cause even more intense hurricanes. We may get hurricanes similar to the past, but they may even be more intense because of the warming that's gone on.
Imagine Boston in the near future, a crowded city, much of it at sea level. Some 7,000 miles to the east, a disturbance forms in East Africa. The ocean, the atmosphere, the temperature, the combination hits. What was once considered by this city's residents as unlikely is about to occur, like it has in the ancient past. Unwittingly, those of us who may have contributed to conditions for the hyper-hurricane may stand in its path. Since the mid-1990s, scientists have been recording a new cycle of increased hurricane forces in the Atlantic. Ancient evidence tells us that these cycles have happened before. Current records warn us it's happening again. Based on these new discoveries, here is a hypothetical scenario of a hyper-hurricane strike. The near future. The Atlantic is warm. Upper winds are light, a now frequent condition. A storm is brewing off North Carolina. But this is no Category 2 Isabel, nor a Category 3 Katrina. This one is sustaining its winds at 200 miles per hour, drawing power from the ocean. This hurricane has reached Category 5. It is then that it makes landfall.
Soon as you breach the building, the air can get inside the building and it'll lift the roof just like it's a wing on an airplane.
The sea off North Carolina responds to the hurricane's low air pressure, rising over 18 feet to fill the void.
And all the wind is basically pushing all that water up on the shore.
With North Carolina paralyzed in its wake in less than 24 hours, the hurricane veers to the north. Towns as far as 200 miles inland could feel the punch. Tornado-like winds, known as mini-swirls, inside the storm, devastate individual buildings. Miami's National Hurricane Center and the Canadian Hurricane Center in Dartmouth, Nova Scotia, sound the alarm to points north. Evacuate. Essential services, transportation, electrical grid, all disabled. A hurricane's forward speed, typically 10 to 12 miles per hour in the tropical Atlantic, now increases dramatically. High-altitude winds drive the hurricane up the seaboard at up to 60 miles per hour.
Rather than having a couple of days to evacuate people, it cuts it down to a couple of hours. A storm can make it from North Carolina to New York in about 8 hours.
With gusts in the region of 140 miles per hour, an object swept up by the storm can take on speeds approaching that of a high-speed train. In many towns, water levels rise 12 feet in 1 hour.
The killer really is the amount of water that accompanies those events both from the sky and from offshore.
As it hits Virginia, the hurricane goes extratropical, covering a wider swath as far inland as Pennsylvania.
If it moves into an area of that strong temperature difference or front, then you can get a very strong extratropical storm. They typically get larger in size.
Boston, Massachusetts. Much of it very near sea level. The proximity of this major city to the coast makes it vulnerable to future storm surges generated by these huge extratropical storms. Most of us don't regard Boston as a prime target for the fallout from future hurricanes. But if the predictions scientists are making are true, all that could change. Our climate is warming. This city and the rest of America's East Coast may face a worrying future as a result. Escape routes from the coast to Pennsylvania, jammed or flooded. There's no way out. The Earth's rotation affects the hurricane's trajectory, accelerating it toward the pole and forcing it slightly eastward. More than 620 miles wide, the storm cuts a swath through Nova Scotia before weakening over the North Atlantic. Off the beaches, permanent new coastal features and inlets are formed. Greater Boston and 60 miles inland sits under 10 feet of brackish water. The flooded Northeast begins to ponder reconstruction. Then the cold water wake of the hyperhurricane warms quickly enough to sustain a new storm, spinning 100 miles to the east, just as Isabel followed in Fabian's wake in 2003. Only this time, it's about to strike an already crippled coast. This is just one hypothetical scenario, but with global warming, the hyperhurricane may wreak havoc on the world we have helped to shape. Hopefully, with continued advances in detection, prediction, and damage prevention, we will be better able to guard against the rage of the coming storm.